Hello class, this is Mr. Roberts at Shasta High School, and I'm going to be stepping us through the preview test that I released for Chapter 2. And the first question says, given the equation of the line, or no, give the equation of a line that matches the given information. So I'm going to give you some information, and you need to give me an equation that will match that information. Let's start with part A. Part A says this line has a y-intercept of 7/8 and a slope of 2/3, negative 2/3. So I know that in order to write the equation of a line in slope-intercept form, I need two parameters. I need to know the slope parameter and I need to know the y-intercept parameter. Well, it turns out this problem's giving me both. It's telling me that my y-intercept, right, my y-intercept parameter is at 7/8, and it's also telling me that my slope parameter is negative 2/3. So with that information, I can write the equation of the line. My line is y equals negative 2/3 times x plus 7/9. The next equation does not give me my y-intercept parameter, but it does give me my slope parameter. So at the start, I know what my slope is, and it also tells me a point that lives on this line. And when I'm told a point that lives on the line, I have to understand that I'm given both an x value and a y value, and x is 12 and y is 4, that is on the line. So again, I'm going to start with the same y equals mx plus b. The y value from my point is the number 4, so I'm going to substitute that in. My slope is 3/4, and my x value from my point is the number 12. And then I have plus b. What I'm going to do is multiply 3/4 times 12. And I can think about it like this. 12 divided by 4 is 3, and 3 times 3 is 9. So you can verify that on a calculator, but 3/4 times 12 is 9. So 4 is equal to 9 plus b. And if I take away 9 from both sides, subtracting 9 from the right-hand side leaves me with just b. And when I take away 9 from the left-hand side, 4 minus 9 is negative 5. So I now know both my slope parameter and my y-intercept parameter. My y-intercept parameter is the number negative 5. My y-intercept was 3/4 or 3/4. So now I can write the equation of the line. For b, it is y equals 3/4 x and then minus 5. Before I move on, just as a check, I'm pointing out to myself that yes, this line that I've written does have the correct slope. It has a slope of 3/4. And also, when I plug 12 in, when 12 is the input into this function for x, 3/4 times 12 is 9, and 9 minus 5 is 4. So when I plug in 12, I did verify that 4 comes out. So this is the correct line. For question C, I'm given 2 points and asked to find the equation of the line that would go through those 2 points. When I do this, I prefer these days to stack the points. So I'm going to write 2/8. That's the first point that was listed. And the other point was 6/4. And then I remind myself that slope is the change in the y variables divided by the change in the x variables. And I can see that my y values are here, right? I've got 8 and 4. And I can see that my x values are in this column. I've got a negative 2 and a 6. So if I write the change in y, I can just go ahead and write 8 minus 4. And you can see I'm just taking the top y value, subtracting the bottom. And then for the change in x, I'm just going to take negative 2 and subtract 6. I'd follow the same pattern, top x value minus the bottom x value. So for my slope, I end up getting 8 minus 4 is the number 4, and negative 2 minus 6 is the number negative 8. So my slope appears to be 4 over negative 8, and if I was to simplify that, I could write that my slope is negative 1/2, down 1 over 2, because both 4 and 8 have a common factor of 4. So if I divide both by 4, I get negative 1/2. So I now know my slope parameter, but I still need to figure out my y-intercept parameter. To find that out, I'm going to go and do the same thing I did in the previous few problems. I'm going to write y equals mx plus b. It does not matter which point that I pick. I have 2 points I could select. I'm going to go ahead and pick this point, and this point does have an x value that is 6, and it has a y value that is 4, and I'm going to use those to replace x and y in this equation that I've written below. So I'm going to go ahead and bring in a y value of 4. My slope parameter was through negative 1/2, and the x value for my point is 6, and then plus b. So when I multiply negative 1/2 times 6, I get the number negative 3. So 4 equals negative 3 plus b. If I add 3 to both sides, when I add 3 to the right-hand side, negative 3 plus 3 is 0. So I'm left with just b. And when I add 3 to the other side, I'm left with the number 7. So my y-intercept parameter is 7. Now that I have both parameters, my slope parameter and my y-intercept parameter, I can write the equation of the line. It is y equals negative 1/2 x, and then plus 7. Before I move on, a really good check is just verifying that when I put in, for example, negative 2, I better get 8, and when I put in 6, I better get 4. Negative 1/2 times negative 2 is positive 1, and 1 plus 7 is 8, so it checks for the first point. And for the second point, negative 1/2 times 6 is negative 3, and negative 3 plus 7 is positive 4. So it checks for both points, so I'm sure that this is the equation of the line that goes through those 2 points. For question D, we're given a table, and a table really just means I'm given lots of points. So instead of just given 2 points, I'm giving 4 different points here, 4 different x and corresponding y values. I can't tell what the y-intercept is from this table. It's not organized, and it wouldn't be simple for me to extend the pattern. So what I'm just going to do is arbitrarily select 2 of the points, and I'll go ahead and use I guess I'll use the last 2. So if I do that, I know these are my y's and these are my x's. So my change in y value, not change in x, my change in y value is going to be, I'm going to write 8 minus and then negative 25. And my change in x value, I'm going to write negative 6 minus 5. So looking at my slope, my numerator, 8 minus negative 25, is positive 33. And negative 6 minus 5 is negative 11. So I end up getting a slope of 33 over negative 11, which is negative 3. So this is decreasing by 3 each time x increases by 1. So I know my slope parameter, it's negative 3. Now I need to figure out what the y-intercept is. It doesn't matter which point I use. I can use any of these points. I'm just going to arbitrarily decide to use the top point. So I can go ahead and write y equals mx plus b just as a reference for myself. My y value from the point I've selected is 35. My slope parameter is negative 3, and my x value is negative 15. And I'll go ahead and write plus b. So when I multiply negative 3 times negative 15, I believe I get positive 45. So y equals 45 plus b, and I'm going to subtract 45 from both sides. When I take 45 away from the right hand side, I'm left with b. And when I take away 45 from the left hand side, I'm left with negative 10. So I believe that my y-intercept parameter is at negative 10. Now that I know both, I can write the equation of this line. It should be y equals -3 times x and then minus 10. And I can verify this by just grabbing a couple of these x values and plugging them in. For example, if I plug in -2, I have -3 times the x, -2, which is +6, and 6 minus 10 is -4. So I see it works on the first point. The next point there, if I take -6 and plug it in, -6 times -3 is +18. Nope. Yeah, it is +18. -3 times -6 is +18, and 18 minus 10 is 8. So it works for both of these points. And I could do this for all of them. I don't need to do it for all of them. I just want to, it's smart to check it for a couple of points. It's possible that you can get an equation that only works for one of the lines. So trying it with two of them is the best possible procedure. If you've got three or more, you can check it at multiple points for sure. The last question on page 1 asks us to report back the output of the function when we are given the input. So here I'm telling you what goes into the function, and the question is what has to come out of this function. Really good technique is when you do the substitution, use parentheses. So I'm going to go 2 and then open parentheses, something gets squared plus the number 18, and then I'm going to divide that entire result by 12. Well, the something that's going into this function, right, is the number 3. So I'll place 3 here, it's my input. So I have 2 times 3 squared. Order of operation, 3 squared is 9, and 2 times 9 is 18. So this numerator is 18 plus this other 18, and my denominator is the number 12. Well, 18 plus 18 is the number 36, and 36 divided by 12 is the number 3. So I know when 3 goes into this function, 3 is spit out by this function. Okay, let's move on to part B. Part B, my input here is -4. This really is illustrative of why it's good to use parentheses. So here my function says x is going to get squared, right? My input value is going to get squared, and then I'm going to subtract 4 times the input value. So -4 is going into this function. When -4 lands in for the first x, right, I have a -4 here. And then -4 is also going to land into this other x. I have a -4 here as well. When I take -4 and square it, that becomes the number +16, right? -4 times -4 is +16. And then -4 times -4, this is also going to be +16. So I end up having 16 twice. And when I combine 16 plus 16, I get exactly the number 32. So the output of this function is 32 when -4 is placed into it. That's the end of page 1. Okay, moving on to page 2, question 3 says identify the input that will produce the given output. So this question's kind of the reverse, or it's the opposite of the ones on the last page, because in this case I'm asking you what value of x, right, that would go into this function and make this function give you back a value of 55. So again, this is the definition of the function, right? That is the definition. It's 7 minus 3 times the quantity of 2x minus 4. And I want to know, right, I want to know what x is going to give me that. So what I do is I just take the definition, 7 minus 3 times the quantity of 2x minus 4, and I'm going to set that equal to the output that I want, right? I want to know what value of x is going to make that thing become 55, and I'm going to solve this for x. I'm going to begin by rewriting this using the distributive property. I can do that. That's going to be, there's still going to be a 7, but then I'm going to have a -3 times a 2x, which is 6x, and then I've got a negative 3 times a negative 4, which is plus 12. That equals 55. So I've just rewrote this so that I no longer have this negative 3 to distribute across this subtraction problem. And this is what it becomes. I can combine 7 and 12, which would give me 19. So 19. So 19 minus 6 times x is 55. I now need to take the number 55 and I'm going to subtract 19 from both sides here. And it turns out 55 minus 19 is 36. So I've kind of run out of room, but I can write over here that negative 6 equals 36. Again, what? No, not negative 6. Negative 6 times x. So again, what I did was I subtracted 19 from the left side and 19 from the right side, and I get this new equation. And then finally, I'm just dividing both sides by negative 6. It turns out negative 6 times x divided by negative 6 is just x. And on the other side, 36 divided by negative 6 is negative 6. So when x is negative 6, it should make this function equal 55. It's definitely worth checking that to make sure it works. If I come in here, I can say, well, this is going to be the number negative 6 minus 4, and then I'm going to multiply that by a negative 3, and I got a 7 here. So if I begin on the inside parentheses, this is negative 12, and negative 12 minus 4 is negative 16. And if I multiply negative 16 times negative 3, I get positive 48. So this problem becomes 7 plus 48. And guess what 7 plus 48 is? You got it. It's exactly 55. So when x is negative 6, it makes the output 55. So I'd write negative 6 here. Let's do the same thing for b. b ends up being quite nice, right? The function is called f of x, and this is its definition. And I want to know what value of x makes this become 12. So I just say, oh, 3x, I want it to be 12. Well, that's super simple, right? Divide both sides by 3, x is 4. So what I'm saying is that when I put the number 4 into that function, right, when my input is 4, it gives me an output of 12. Yeah, because 3 times 4 is 12. So that number 12 would go over here. That's my answer for 3b. All right, let's move on to question 4. Question 4 has some expressions, and we're asked to simplify them. The first one, let's see. Let's zoom in a little bit here on this and take a closer look at it. So I am multiplying the number 7, right? The number 7 times two expressions that involve just x and y. And I can see it's only multiplication. There's no addition, subtraction inside of these. So I can start by thinking about I'm multiplying 2 factors of x, that's x, times 4 more factors of x. When I do that, I end up with 6 factors of x, right? That's xx times xx, xx. So part of my answer is certainly 7 times x to the 6th power. And then I have to process the fact that I've got some factors of y. This is y to the negative 4th times y to the 9th. That negative exponent took care of itself because this is just going to become y to the 5th power, right? Negative 4 plus 9 is y to the 5th. So this becomes 7x to the 6th, y to the 5th power. All right, let's look at part B. You can see it. It's got a negative exponent. My favorite preferred way of getting rid of that is to multiply it by a number such that this negative exponent will cease to be a thing. And I'm going to multiply this precisely by x to the positive 3rd. The reason why I selected x to the positive 3rd is I know if I multiply x to the negative 3rd times x to the 3rd, I get x to the negative 3 plus 3, which is, you got it, x to the 0, which is always the number 1. So in selecting x to the third to multiply this denominator by, I get 1. Now, I have to be careful. I could only multiply by the number 1, right? So I have to put 3 factors of x in the numerator to compensate for the fact that I just threw 3 in the denominator. So this thing right here represents the number 1. That's what I'm multiplying by. And I know that in my denominator, I created a number 1 here, right? X to the negative third times x to the third. So what I'm left with at this point in the numerator, I've got the number 12. And I've got now 1, 2, 3, 4, 5, 6. I've got x to the 6th power. And in my denominator, I just have the number 4. And the last time I checked, 12 divided by 4 is pretty straightforward. I could simplify that. That's 3x, and it's raised to the 6th power. So that's the answer for part B. Please make sure you write those in the line spaces provided over here, right? So I'm expecting to see the 7x to the 6th, y to the 5th here, and this should be, what was it, 3x to the 6th, 3x to the 6th power. All right, let's move on to part C. Aha! I got another negative exponent here. This will be fun. This will be fun because it's actually just like the last problem. I'm going to multiply this by b to the 3rd power in the denominator. And to make sure this is just the number 1, I'm going to put b to the 3rd in the numerator also. So I'm completely satisfied with the fact that this equals 1. In my numerator, I have a to the 5th power, b to the 8th, b to the 5th times, a to the 5th times b to the 8th. And in my denominator, I just have a to the 3rd power. So not done, because I can see that I've got a couple common factors of a living in both the numerator and denominator, and I need to take care of those. So let's do that. I could think about it like this. This a to the 5th is the same thing as a to the 3rd times a to the 2nd. That legitimately is a to the 5th. Then I've got a b to the 8th power, and down below I've got a to the 3rd. So this is equal to 1, so it's gone. And my final answer is a squared b to the 8th. And I would definitely write it on this line right here for C, a squared b to the 8th. Okay, last question on this for problem 4 is part D. And part D, I've got something in parentheses being raised to the negative 2nd power. I'm not the least bit concerned about this, because what I'm going to do is I'm going to multiply the top by 2x to the 5th raised to the positive 2nd power. And in the denominator, I'm going to do 2x to the 5th to the positive 2nd power also. When I do that, right, this product in the numerator is going to become 2x to the 5th raised to the 0 power, which is equal to 1. So my numerator is nothing but 1. My denominator, right, is just 1 times 2x to the 5th and then squared. Now the simplest form would call for me to go ahead and square that. So I am going to square 2x to the 5th. There's a couple ways I can think about it. I can just expand it. That's 2x to the 5th times another 2x to the 5th. When I multiply 2 times 2, 2 multiplied by 2 is the number 4. And when I multiply x to the 5th times x to the 5th, that's 5 factors of x times 5 more factors of x. So this is a total of 10 factors of x. So my final answer is going to be 1 over 4x to the 10th power.
Let's jump to question number 5. In 5, there's 2 parts, and we're asked to solve an equation. Solve 2 different equations. So the first equation, I noticed that there's a chunk of it that could probably be very well rewritten using the distributive property. So what I'm choosing to do is rewrite this, except I'm going to get rid of the parentheses, by distributing this 4 across the subtraction problem. So this will become 2x plus 1 plus 4x minus 8. That will equal 11. So you'll notice that I multiplied the 4 times the 8, and I also multiplied 4 times the negative 2. I'm sorry, 4 times x and 4 times negative 2. Looking forward, I can see that I have some like terms on the left-hand side. I'm going to choose to combine those. I will get 6 times x. I also have a pair of constants on the left-hand side. I'm going to combine those as well. 1 and negative 8 will make negative 7. And over on the other side, I have 11. I'm going to add 7 to each side of this equation. When I add 7 to the left-hand side, I get 6 times x. And when I add 7 to the right-hand side, I get 18. And then finally, I'm just going to divide both sides by 6. X will be 18 divided by 6, which is the number 3. It's very nice to kind of verify that 3 actually works. So I'm going to place 3 in 2 places. 2 times 3 is 6. Plus 1 plus, let's see, this is going to be a 3 minus 2, which is 1. 1 times 4 is 4. And sure enough, 6 plus 1 is 7. 7 plus 4 is 11. So when I placed 3 in, it made the left and the right hand side both 11. So this is indeed the solution. I'll write over here that x is the number 3. Let's move on to part B. B also has some values that I can distribute. So the first thing I'm choosing to do is to distribute the negative 3 across this addition problem of x plus 2. And I'm also going to distribute this 6 across the subtraction problem, x minus 5. So when I rewrite the left-hand side, it's going to become 4x minus 3x minus 6, and then plus 11. So you see that I multiplied negative 3 by both x and by 2. On the right-hand side, when I distribute the 6 across the subtraction problem, I get 6 times x and then minus 30. So now taking a look at the left-hand side, I can see that I have a couple of like terms, and a pair of them are x's. I've got 4x minus 3x. Those can be combined. And I also have a negative 6 and an 11 that can be combined. 4x minus 3x is just simply x. And then I have minus 6 plus 11, which would be positive 5. Over on the right-hand side, I have 6 times x minus 30. I'm going to choose to get my x's over on the right-hand side. So to accomplish that, I'm going to subtract a single x from each side. When I subtract 1x from the left-hand side, I'm left with just the 5. And when I take away a single x from the right-hand side, I'm left with 5x, and then the minus 30. Next, I'm going to add 30 to both sides. 5 plus 30 is 35, and that is 5x. And when I divide both sides by 5, I get that 7 is the value of x. So taking a look at this and checking it, 4 times 7 is the number 28, so I'll write it 28 here. If this is 7, 7, 8, 9, 3 times 9, let's see, 3 times 9 is 27, so this is 28 minus the number 27, and then plus 11. Well, 28 minus 27 is 1, and 1 plus 11 is 12. So I've got 12 sitting on the left-hand side. On the right-hand side, when I put 7 in for 5, this becomes 7 minus 5, which is 2, and 6 times 2 is 12. So I can see that, yes, indeed, when I place 7 in both the left and the right-hand side, it does make both sides of that equation 12. So x is the value 7, and I will record that over here as well. X is 7. For question 6, I am asked to evaluate a couple expressions, and I am given values for variables that I'm going to be plugging in. I can see what A, B, and C are. So if I take a look at this and I plug in A and B, I probably am going to go a little crazy with the parentheses, but I've got a 2, and inside of these original parentheses, I've got a negative 3 that's my value of A, and then plus 2, that's the value of B. I'm going to close those, and then I've got a plus 5. In the denominator, C is the number 2, and I've got a 1. So taking a look at the numerator, when I combine my -3 and 2, that's -1. -1 times 2 is -2. So my numerator will rewrite as -2 plus 5. My denominator is the number 3. If I combine -2 and 5, I get 3. So this becomes 3 over 3, which is just the number 1. So when I plug these values in, when I plug in the value A is -3, B is 2, and C is 2, this expression becomes 1.
Let's continue on with part B. In part B, we are asked to evaluate the expression B plus C quantity squared plus 4 minus 5C. So it turns out I don't need A this time, I just need B and C. And again, I will use the parentheses to organize my work. So for B, I'm going to place the value 2. C is 2. And I'm going to square this. Then I have plus 4 minus 5 times the value of C, which is still 2. When I combine 2 plus 2, I get 4. So I could say that this is the value 4 squared, which is 16, plus 4, plus 4. And then -5 times 2 is -10. So I am going to be subtracting the value of 10. So when we combine 16 and 4, we have 20, and 20 minus 10 is the number 10. So this becomes 20 minus 10, which is 10. So for part B, when I evaluate this expression, when B is 2 and C is 2, I end up getting the number 10. And we are on to our final two problems, which involve dimensional analysis. One of them, we have to convert both units in a rate, and the other one is just one of the two units in a rate. So let's take a look at this. The problem says the Hubble Space Telescope travels in orbit around the Earth at 308,000 inches per second. Convert this rate of travel into miles per day. So we have the target we're looking for. We want our distance to be miles and our unit of time to be days. And you can see we've got inches per second. So let's go ahead and write the 308,000. And it is per 1 second. So I'm going to write that, and I'm going to write my units are inches per second. And now I'm ready. I am going to choose to deal with time first. So I'm going to move seconds into days. And I can do that in a few jumps. I happen to know some giant ones, and I think most of you know these as well. If I want to get rid of seconds, I could put seconds in the numerator, and I could put minutes in the denominator. And I happen to know that 1 minute is the same amount of time as 60 seconds. So the big idea here is that I just multiplied this by the number 1. Therefore, I haven't changed the speed at all. I'm just changing units. I'm going to do the same thing now. I want to get rid of minutes, and I happen to know that 1 minute is the same amount of time as, not 1 minute. 1 minute, I was going to go to hours here. Minutes, hours. It turns out that 60 of those things I call minutes is equivalent to 1 hour. So again, these are both equal amounts of time. 60 minutes is the same as 1 hour, so I'm just multiplying by the number 1. Again, I'm going to multiply by another number 1. I want miles. Wait, I want miles per hour, don't I? Do I want miles per hour? No, I want miles per day. So I needed to get rid of the hours. So I'm going to go one more jump. I'm going to put hours in my numerator. And again, I'm putting those there because I can see I had hours in the denominator. And I probably should have pointed that out sooner. And it turns out that if I'm jumping with hours and days, 24 of those things we call hours are equivalent to 1 day. And this is the final giant one I need to multiply by to deal with time. So let's take a look at the units that we have, right? Our seconds canceled with these seconds. Minutes are gone with these minutes. And these unit hours are gone with hours. So what I'm left with, and I'll circle these in blue, I've got this number, 308,000. I've got 60. I've got another 60, and I've got 24. So those are the numbers that I have in my numerator. And to find the answer, I know I'm going to multiply those, but I'm not quite done. That is it's a pretty large number, and that number is in inches per day. So I'm just going to say, I'm just going to bring that number down, and I'll put it in this box, but not yet. I'm not going to do it yet. I'm just going to write instead that I've got inches per day. That's what I'm starting with, right? I've got inches per day. And I need to jump to miles. From inches, I need to jump to miles. And I think there's just a couple of jumps that are necessary there. One of them is, well, of course, if you look, I've got inches in the numerator, so I want the inches to go away. That's why I'm placing them down here. And I'm going to jump to feet. And I happen to know that 1 feet or 1 foot is the same distance as 12 inches. Again, the big idea is that is equal to the number 1. So I'm just changing units. I'm not changing the value. But right now I'm going to have, this would be feet per day, right? If you look at it, because these inches are going to cancel. And then the last thing I'm going to do is introduce the conversion factor for miles. And it turns out that I want feet to go away, so I'm going to place feet down here and miles where I'm going. And it turns out that 1 mile is 5280. I just have that memorized and I say it like that. That's probably a conversion factor that I'll have on the whiteboard if you require it. 1 mile is the same thing as 5,280 feet. Most of these with time, I kind of expect that you'll know those and be able to deal with that. But 1 mile, 5280, I probably will write that on the whiteboard so you can look up and see that. So if you look at where we're at now, right, you can see that my inches have canceled with inches. My feet have canceled with feet. And the only units I have left, right, after considering both the top and bottom, is in my numerator I've got miles, and in the denominator I have days. So I'm looking at miles per day. And now let's talk about the arithmetic we have to do, right? Because there's a number up here. The number in the numerator is 308,000 times 60. I don't have enough room to write this. 308,000 times 60 times 60 times 24. So you can see I got that number, that number, that number, and that number. And in my denominator, I have the number 12, and I have the number 5,280. So I've got these two numbers. So now it's just a matter of doing some arithmetic with my calculator. So on my calculator, I'm going to take 308,000 times 60 times another 60, and then times 24. So I have a very large number on my calculator display. I've got 26,611,200,000, and I need to divide that by 15 times 5280. So unfortunately, I'm not in scientific mode. Can I switch to it without? Oh, I lost my number. So I've got it back on the display. Now that I'm in scientific mode, I can say divided by, but then I need to open a pair of parentheses so that I can multiply both 12 times 5280. So I need 5280. There we go. And then close the parentheses. So I'm dividing by 63,360. And when I do that, I get 420,000 miles per day. 420,000, 1, 2, 3, and these are miles per each day. All right. Moving quite fast. All right, so last problem here, question 8, it's a similar problem, but this is obviously a little bit more, it's a little less intense. And if you'll notice this one, I'm given a measurement in gallons per week, and I'm asked to convert that into gallons per hour. So the only thing I really need to focus on is the conversion of weeks into hours. So less work, I can do this in one line. I've got 125 gallons per week. I'm going to go ahead and put this over 1. I'm going to multiply that by, let's see, I'm going to put a week in the top. It turns out a week, I can write a fact with days, right? 1 week is the same thing as 7 days. So I can see that I've effectively canceled out my week units. And same thing with days, I'll have days in the numerator. And I can go to hours, and it turns out that 1 day is the same thing as 24 hours. So now my units of days are gone as well. So the only units that remain are gallons per hour, which is exactly what I want. So I can write that down. It's gallons per hour. And my number in the numerator, I have 125. In the denominator, I have the product of 7 and 24. Let's see, I'll do this off screen. 7 times 24 is 168. So I've got 125 divided by 168 and 125 divided by 168. It looks like about 0.74. I'm going to round my answer to the nearest. I'm going to round it to the nearest hundred. So I'm going to round this as 0.74 gallons per hour. So yes, if you are going through 125 gallons each week, 125 gallons each week, that means whatever you're doing is consuming about 3/4, 0.75 gallons per hour.